Left off last time, and everybody's going to take a second and predict the product of this Claisen reaction here. And what we discussed last time is not only should we be able to predict the product, but you should also be able to tell me what base we used in order to catalyze this reaction. All right, remember, since we're reacting these two esters with one another, it's very helpful to draw both of them in there and to indicate your nucleophilic site in one of them and your electrophilic site in the other. All right, where's our nucleophilic site in these reactions? The alpha carbon. And where's our electrophilic site? Carbonyl carbon. All right, so there's where my new bond is going to be between my nucleophile and my electrophile. All right, and maybe it's even helpful to kind of list steps here. What we can note is in our both the aldol reactions and our Claisen reactions, our nucleophile appears pretty much as is in our product. We have all of those carbons, all of those atoms represented here. So when we're doing our products, the first thing we want to do is to just redraw that nucleophile. All right, this whole thing is going to appear in my product. All right, and then we want to put in that new carbon-carbon bond. So when I draw from my nucleophile that new carbon-carbon bond, what's going to live on the other side? That electrophilic site. All right. Now, in these Claisen reactions in particular, this ester group here in my electrophile is going to be playing the role of what? A leaving group. So, when we draw in our electrophile carbons, we want to draw those electrophiles, electrophilic, let's say electrophile carbons, just minus that leaving group. So it's only going to be these 3 carbons from my electrophile that will appear in my product. Everything from my nucleophile appears in my product, but only these 3 from my electrophile appear in my product. All right, and then what's my other functional group? We have this carbonyl, really this ester group. What's the other functional group in our Claisen condensations? All right, let's remember what we why we lost that leaving group was because we formed that tetrahedral intermediate, but then that pair of electrons comes back down and kicks off that leaving group. So we reform our carbonyl bond at that electrophilic carbon. All right, so my electrophilic carbon also has this carbonyl group here. All right, and then we talked about what base we would use to catalyze these reactions here. They should match our leaving group of our esters. So this base I'm going to use is this alkoxide ion, always going to be this oxygen with a negative charge. But specifically, I'm going to want to use this 3-carbon base here so that it matches my leaving group. Right, so we can just note our base is going to match that leaving group. Cool, and so this is where we left off last time. We can predict our products of our Claisen condensation reaction, and we know that our base should match our leaving group for that ester. All right, now we're going to talk about our solvent that we're going to use. Okay, so let's just say that we took that base and we used a solvent of H2O. All right, well, what's going to happen when that base reacts with water and deprotonates it? We're going to get an alcohol and a hydroxide ion. All right, and as we discussed last chapter, these hydroxide ions react with carbonyl carbons in aldehydes and ketones. Same thing in esters as well. So we would end up getting this side reaction that we don't want if we tried to use water as our solvent, because we would create some hydroxide that would just end up reacting with our aldehyde or with our esters as well. So when we are clever in selecting our base, we're also clever in selecting our alcohol, where we want our alcohol to also match that ester leaving group. So I'm going to use that same 3-carbon, in this case, alcohol. All right, and why am I going to be doing that? Well, let's say that this also reacts with our base. Everybody take a second and draw me the products of this reaction. All right, what's my product going to be? Same thing. If isopropoxide reacts with isopropanol, I get isopropanol and isopropoxide. All right, so our alcohol that we're going to use, our solvent, is going to be an alcohol that is our protonated base. All right, should also match that solvent, should also match that ester leaving group. So in this case, my solvent is again what we would call isopropanol, or 2-propanol. All right, and then lastly, to discuss with these, in these aldol addition and Claisen condensation reactions, kind of been being lazy, this is the first step. There's always this second step where you do this acidic workup. And this is not necessarily super obvious as to why you would do this second step, because if you looked anywhere in our mechanism, we don't have any proton transfer that we need to do at the end here, right? We're not needing to protonate this, in our mechanism here. You follow it along. There's no need to sort of protonate to get to that final product. So why would we want to do this proton transfer, or why would we want to do this acidic workup at the end? All right. All right, so sort of simply put, it would be to just help to neutralize your solution, right? We started out with this very basic solution of an alkoxide in alcohol, but especially with our Claisen condensation reactions, it plays a very important step. All right, so let's just answer, why do we have to do an acidic workup? All right, well, let's take a look at our sort of simplest Claisen reaction here. Meaning I want to look at one with some fewer carbons so we can see a little bit easier what's going on. Okay, this was our first example that we did. Let me get rid of these sort of color codings here. And we can note we said that this was our base that we're going to use. So everybody's going to take a second and complete their chemical equation by drawing in the alcohol that we should be using. Our solvent. All right, if we use in 1 carbon alkoxide, what should we use for our alcohol? A 1 carbon alcohol, and hopefully everybody knows that this is methanol. All right, but that's step 1 here, and like we said, our last step is going to be this acidic workup, but why? All right, so our base was doing what in this reaction? What was our base reacting with? What's that first step? The hydrogen. So what is that base doing? It's reacting at what site? Title of the chapter. Alpha carbon. And what's it doing to that alpha carbon? It's deprotonating that alpha carbon, right? And the whole shtick about this alpha carbon chemistry was that those alpha carbons are relatively acidic, right? We can remove them to create those nucleophilic enolate ions. Well, in my product of a Claisen condensation, do I have any alpha carbons in my product? Yes. And in fact, that alpha carbon has not 1, but 2 carbonyl groups there. And remember, if we have 2 carbonyl groups, that means that that enolate ion is even more resonance stabilized. So that hydrogen is even more acidic. Look at what happens to our pKa, dropping from a pKa of 20 to a pKa of 9 when I have those 2 carbonyl groups there. So I have this alpha carbon that was even more acidic than when I started out. All right, so at the end of that first step, I create my product here, but that'll again just react in that basic solution to be an enolate ion. Right, so after step 1, that alpha carbon is even more acidic and will be deprotonated. So I need to do this acidic workup step. I need to add in some dilute base just to protonate it to give me my neutral product. All right, that'll protonate that carbon to produce our neutral product. Okay, so in our Claisen condensation reactions, we start out with an ester. We're going to treat it with a base in some solvent, and we're going to be really clever about our choice of base and solvent so that they match the leaving group for that ester. And then we're going to have to follow it up with some acidic workup step because our product is an even stronger acid, creating that deprotonated alpha carbon. So if we want to get a neutral product at the end, we have to add in some dilute acid to do it, right? We can't stay under those very strongly basic conditions. All right, so now we're going to talk about what we call mixed aldol and Claisen reactions. All right, so this is when we do an aldol addition or condensation reaction or a Claisen condensation reaction, but using two different substrates here. All right, and what we're going to find is that we can't just use our same conditions of just adding in, so for example, for our aldol additions, adding in sodium hydroxide. All right, because we'll end up getting a mixture of products. I guess that's not to say you couldn't do it, it's just if you do it, you would get this complicated mixture of products. All right, so why is that? Why am I going to get a mixture of products here if I just mix this aldehyde and this ketone together under basic conditions? What's the nucleophile in these reactions? The alpha carbon. All right, which one of these has an alpha carbon? Both of them do, right? And what's the electrophile in this reaction? The carbonyl carbon. And which one of these has a carbonyl carbon? Both of them. So if you just tossed all these together, you wouldn't be able to control what's playing the role of the nucleophile and what's playing the role of the electrophile. You would get a mixture of both, right? Sometimes this aldehyde would play the role of a nucleophile. Other times it would play the role of the electrophile. Likewise, sometimes your ketone playing the role of the electrophile, other times the nucleophile. Not only that, but you couldn't sort of control them reacting with one another. You would get reaction of that aldehyde reacting with itself, where one of them's playing the role of the electrophile, the other one's playing the role of the nucleophile, and the same thing for our ketone as well. Right? This would react with itself, sometimes playing the role of the electrophile, other times playing the role of the nucleophile. All right, so we get a mixture of all four of these possible products. So if I wanted to control this in a way where I wanted to make sure that one of these was my nucleophile and the other one was my electrophile, I couldn't just add them in all in one shot in those basic conditions. I'm going to have to first convert my nucleophile into that nucleophilic form, into that enolate ion. Okay, so we want to efficiently create our enolate ion. We're going to call it that enolate nucleophile. All right, but what choice of base should we use? Okay, so the base that we've been using thus far is just simple sodium hydroxide. And of course, whenever I see a sodium in a salt like this, what am I going to do? I'm going to erase it, and what am I going to replace it with? In this case, my oxygen would have 3 lone pairs, but yes, replace it with a minus sign. Okay, so this reaction here creates this, if we're looking specifically at our acid-base reaction. Okay, we're going to deprotonate that ketone to create our enolate ion. And then what would my other product be? Hydroxide is going to react, and what's the hydroxide going to become? Water. All right, so all the way back in the first semester, we talked about how we could predict the direction of equilibrium in this reaction. Does it favor the products, or does it favor the reactants? By comparing the pKa of your acid to the pKa of your conjugate acid. So we looked at these earlier. We made a table here. The pKa of these ketones is around 20, and the pKa of water is around 16. So which one of these is the stronger acid, water or our ketone? Water, right? Lower pKa means stronger acid. Well, if water is the stronger acid, that means it wins, meaning that it is going to be the acid. This reaction here favors our reactants. And in fact, this 4-point difference in pKa here, devil's in the details in terms of your concentration of base, but roughly speaking, means that 99.9% of that organic molecule would remain in that ketone form, and only 0.1% would be converted to these enolates. All right, so is this a very efficient reaction for creating enolate ions? No, 0.1% of your product would not be considered very efficient. All right, now, does that matter when we're doing something like an aldol condensation or aldol addition reaction? No, because we don't really need this equilibrium here to strongly favor these enolate ions. I don't need a full beaker full of enolate ions. If only a small fraction is converted to nucleophile, that will react with the other ones and then get stuck over here on the product side. So this reaction might not be the fastest thing in the world, but I don't need that first step to be all that efficient in order to create a nucleophile and then quickly get trapped over here in these irreversible steps. But if I'm trying to do one of these mixed reactions here, this is not going to work. This is not going to be an efficient way for creating these enolate ions. So instead, we got to use some super strong bases. All right, of course, in general chemistry, we were calling hydroxide a strong base, but in the world of organic chemistry, there are plenty of other acids that are too weak to be deprotonated by that base. We got to use something even stronger than hydroxide. All right, so our super strong bases that we can use here, one of them we've seen, both of them, rather, we're going to have two of them. One of them we've seen before, sodium hydride. These are used to very efficiently deprotonate alcohols. They can also be used to efficiently deprotonate ketones. Of course, that sodium isn't doing anything. It's that negatively charged hydrogen that's playing the role of the base. And if we took that same aldehyde or ketone, I'm just going to use acetone for right now. All right, and instead we put this in with sodium hydride. We wouldn't even use our equilibrium arrows here. We would just use this one forward arrow because now we have created these enolate ions with near 100% efficiency. Right? At the end here, I have 0% in that ketone form. Everything's been converted to those enolate ions. All right, if instead I wanted, rather another one that we can use is what's called LDA, or lithium diisopropylamide. Okay, again, the lithium's not doing much for you here. The key is this amide, this negatively charged nitrogen. It's got these two big isopropyl groups on it. But those negatively charged nitrogens, again, super strong bases. And so same thing, if I were to take acetone and treat it with LDA, I would get this deprotonation reaction, this formation of my enolate that happens with 100% efficiency. Now, in the case of acetone, this is this symmetric molecule. Both of my alpha carbons are identical, so it wouldn't matter which one of these bases I choose. But there is a practical difference between these two bases, and that's just the size of them. So which one's smaller, sodium hydride or LDA? Yeah, just this single hydrogen atom versus this big bulky LDA molecule here. So this one is my small base. This one is my large base. Your small base is going to favor your most, whatever is the most thermodynamically favorable, the most stable enolate, which turns out to be deprotonating the more substituted carbon. Whereas that big bulky base is going to have a hard time getting to the more substituted carbon. So it's going to prefer the more accessible carbon. Now again, for acetone, those are identical. But we can pick an aldehyde or ketone, actually would have to specifically be a ketone, where there's a difference between those two alpha carbons. So let's take an example here, stack these next to each other. So on the one hand, I want you to give me my enolate product if we treated this with sodium hydride. And on the other hand, I want you to give me my enolate product if we treated this with LDA. Right, so again, we got two alpha carbons that are not identical in this reaction here. Our sodium hydride is going to prefer the more substituted carbon. So what is that, orange or green? The green carbon. All right, so that will deprotonate specifically that green carbon, creating that enolate ion. All right, whereas LDA prefers the more accessible carbon, which would be our orange carbon. So both of these are going to efficiently create those nucleophilic enolate ions. They're just going to be selective over which alpha carbon they pick. Again, LDA, the more accessible, and sodium hydride, the more substituted. All right, and we've seen something similar before. That's what we would call our more substituted, our more stable is our thermodynamic product, whereas our more accessible is our kinetic product. And as we saw before, talking about thermodynamic and kinetic products, we can kind of even more selectively take one of these two hydrogens off by tuning our temperature as well. So at high temperatures, we would want to use our sodium hydride. That would make it even more efficiently that more substituted carbon. Whereas LDA we would use at low temperatures to even more specifically favor that less substituted carbon, all right, our more accessible carbon. All right, so practically speaking then, what does this mean? We have different ways of creating different enolate ions. Meaning if I used sodium hydride, this would be my nucleophilic site, my more substituted carbon. And if I used LDA, this would be my more nucleophilic site, my more accessible carbon. All right, so then let's take this same molecule here, and we're going to do two different things with it. First, we're going to turn it into an enolate ion by using sodium hydride at high temperatures. All right, then we're going to follow it up with a different aldehyde or ketone so I can get this mixed aldol product. All right, in this case, we will use kind of just a simple aldehyde here. All right, and then I'm going to do the same thing, but instead create that enolate ion with LDA at low temperatures. And then I'll just follow it up with that same aldehyde. All right, so let's try to do this first one together here. See if we can't figure out what's going on. After that first step of sodium hydride at high temperatures, what am I going to do to my ketone? Deprotonate it, and specifically which one? More substituted carbon, so that would be this one over here. Which means that it is what? A nucleophile or an electrophile? A nucleophile, specifically at that enolate ion. So then when I take that and I follow it up with this aldehyde here, what role is this aldehyde going to play? The electrophile, and specifically at what site? That carbonyl carbon. All right, so we're going to need to do an aldol addition reaction here. Let me actually make some room. As we were doing before, the easiest thing to do is to draw your nucleophile and your electrophile with those proper sites highlighted. So here's my nucleophile. Here's my electrophile. Okay, react these two together to create my mixed aldol addition product. right, so again, we can start by redrawing that nucleophile, since that fragment's going to appear pretty much as is in my product, just with an extra bond. Okay, since I'm going to need to draw more bonds at this carbon, I'm going to space it out a little bit. But here are the 1, 2, 3, 4, 5 carbons in my nucleophile and that nucleophilic site. So now I'm going to draw my new carbon-carbon bond. What lives on the other side must be that electrophilic carbon. And that electrophile had a total of 2 carbons. So there's 1. Here's another one, bless you. All right, and in the case of our aldol additions, my other functional group here is that hydroxyl group. Different from if this was an ester, when I would get a clayson with a carbonyl group. This is not an ester, it's an aldehyde or a ketone, so I'm going to get an alcohol. And we talked about how the spacing should be those 1, 2, 3 carbons apart, and I can convince myself that I have that proper spacing here. So that was if I did this using sodium hydride at high temperatures. Now everybody's going to take a second and give me my product if I did lithium diisopropyl amide at low temperatures. Amide. All right, so again, I'm going to draw in my product of that first step, which is when we deprotonated that alpha carbon, but since we were using LDA, we specifically deprotonated that more accessible carbon. So that's my nucleophile, going to react with that electrophilic carbonyl carbon of my aldehyde here, that second molecule that I added. All right, I can start by redrawing my ketone, my nucleophile, which was the ketone. All right, I got my 1, 2, 3, 4, 5 carbons, and my nucleophilic site. I'm going to draw in my new bond, what lives on the other side, that electrophilic carbon. All right, my electrophile had a total of 2, so I'm going to make sure to put those 2 on there. All right, and then that carbonyl oxygen in an aldol addition becomes a alcohol group. And again, we see that 1, 2, 3 carbon spacing that we would expect in these aldol additions. All right, so notice that depending on which base we use, we can select one or the other alpha carbon, leading to a different product in our aldol addition reactions, right? Sodium hydride selects the more substituted carbon to be your nucleophile. Lithium diisopropyl amide selects the more accessible carbon to be your nucleophile. Okay, and then lastly, because we're doing this sort of mixed reaction here, we can even select what we add in second. In this case, I added in an aldehyde, so I got an aldol addition. All right, but let's just take this same molecule. Oh, one more thing to be good here. We're going to note that in our list, we should also have that last step where we neutralize everything with that weak acid, or acidic workup step. All right, but now let's take this same aldehyde, or the same ketone here. We're going to treat it with one of those two bases. I'm going to do LDA at low temperatures. All right, but now instead of adding in an aldehyde, I'm going to add in an ester. And then I'll do that third acidic workup step. All right, but now that we've changed this electrophile here from being an aldehyde or ketone to an ester, we're going to get a Claisen type condensation product. So everybody take a second and do this reaction here. All right, again, we want to identify our nucleophile. So which one's going to be our nucleophile if we use LDA, the orange or the green carbon? The more accessible orange carbon here will be my nucleophile. All right, what's the electrophile going to be in my ester? That carbonyl carbon. All right, the difference is that we'll have that leaving group get kicked off in our reaction here. All right, so everybody take a second. Now that we have a Claisen condensation here, give me my product, a mixed Claisen. All right, we're going to start by redrawing that nucleophilic, our nucleophile here, all 5 of our carbons. We do our new carbon-carbon bond. What lives on the other side must be that electrophilic carbon. My electrophile's got a total of 2 because I'm going to kick off that leaving group. All right, but whereas in an aldol addition reaction, I had a carbonyl group and an alcohol group, in a Claisen reaction, I'm going to have a carbonyl and what? Another carbonyl. Right? That carbonyl is what reforms to kick off that leaving group. Okay, So in these reactions here, since that first step is to convert this aldehyde or ketone or ester into our nucleophile with 100% efficiency, I can follow it up with whatever electrophile I want, right? That alpha carbon will play the role of the nucleophile, and then I'll have my electrophile. Depending on whether I use an aldehyde or ketone, I would get an aldol addition type reaction. If I used an ester, I would get a Claisen condensation reaction. Okay, so we can mix and match with these strategies of using these super strong bases to create our enolate ions with 100% efficiency. Cool. All right, we'll pick up with this next class period.